Today we're going to talk about single replacement reactions. Single replacement reactions are reactions in which a free element reacts with an ionic compound and replaces one of the elements in that compound. Now it's very important to know what that free element is and categorize it, because the rule is that metals replace metals and nonmetals replace nonmetals. So if you have a situation like this first example where magnesium is being added to a solution of iron 3 chloride. So we've got Mg being added to a solution of iron 3 chloride. Now please remember that iron 3 simply means that iron is a +3, chlorine is a -1, so our formula comes out to be FeCl3. We're going to react that, and magnesium is going to bump out something in that iron 3 chloride. Remember, magnesium is a metal, so metals bump out metals. Magnesium is going to bump out the iron. We're going to be left with metallic iron, free iron. The magnesium is going to combine with the chlorine. Be very careful, guys. It's going to combine with chlorine, but remember, does that subscript carry over when it's not part of a polyatomic ion? No, it does not. We've got to go back up here and find charges on our magnesium. +2 for magnesium, -1 for chlorine, so that means our formula is going to be MgCl2. Now, it doesn't really matter what our uh, charges are, or excuse me, not our charges, but it doesn't really matter what our subscripts are for those chlorines, because think about it. We're adding it to a solution of iron 3 chloride, so we're in water, and both iron 3 chloride and magnesium chloride are going to ionize. They're both soluble. So what happens then? Those chlorides are going to drop out as spectator ions. So what we're actually going to end up with here is Mg plus Fe3 plus, yielding Fe plus Mg2 plus. Now, first glance, this might appear to be balanced, but it's not. The charges are not balanced. We've got it balanced by mass, but not by charge. In our order for those charges to balance, we're going to need 2 iron 3 pluses for every 3 magnesium 2 pluses. So those charges translate then by mass to require 2 free element irons and 3 free element magnesiums in order to get these charges and mass and elements balanced out. So that's our final reaction for that single replacement. Now in the next one, bromine and potassium iodide are mixed. Remember, bromine is Br2, potassium iodide, Ki, potassium's +1, iodine's -1. Bromine is going to bump something out in that reaction, and bromine is a nonmetal, and remember that nonmetals bump out nonmetals. So bromine is going to bump out the iodine. Now in Chem 1 we had to worry about who was capable of bumping out who was more active, but in AP we're not going to have to worry about that because they're not going to give us a reaction that won't work. So this is going to work. We've got iodine bumped out by itself, and now we've got potassium and bromine together. Now the iodine is one of our diatomic elements, so we're going to need a 2 with that. And now remember that we are in a, we're going to assume that we're in an aqueous solution is generally how these reactions are done. So if that's true, then we're going to need to split both the potassium iodide and potassium bromide. They're going to ionize because potassium's compounds are always soluble. So we're going to drop out the potassium on both sides. We end up with, and guys, I know this was a little ambiguous, but if this were the AP test, they would definitely say bromine and a solution of potassium iodide or aqueous potassium iodide are mixed. So you're not going to have to worry about on the AP test. If this were actually a test situation, I would be very specific about that as well. Probably ought to be that way on my notes as well, and I just left that part out, but we're going to assume that it is in aqueous solution so that we know how to do it when it is. So we have iodine splitting like this, going to I2, and then bromide, remember, if it splits, it gets a charge. Now we got to make sure at the very end that we're balancing by mass, and notice that if we've got 2 bromines on the left, we're going to need 2 on the right, and if we've got 2 iodides on the right, we're going to need 2 on the left. So in order to be balanced, this is what we're going to look like in the end. So that's our reaction, or the equation for that particular reaction. Our last example is kind of a specific one, but AP really likes this one. You see it a lot on the AP test, so we're going to look at what happens here. We've got hydrogen gas that's being passed over some copper 2 oxide. This is actually a very practical reaction that they do whenever they're mining copper ore. And if we have this copper oxide and we're trying to get the copper out of it because the copper oxide is pretty much worthless to us, or at least the pure copper is a whole lot more useful than the copper oxide. When we react this, what happens is the hydrogen bumps out the copper. We're going to get pure copper metal. And look at what the only byproduct of this is. It's a very clean reaction. We get H2O as our byproduct. Nothing in here, everything in here is either an oxide or molecular or an element, so nothing is going to ionize. So it looks like it's balanced. So there's our final reaction for that particular, our final equation for that particular reaction.